Okay, here we go. We're going to talk about antiderivatives today. And one simple objective, and that's to be able to compute antiderivatives for elementary functions. Okay, so here we go. First, let's start off with what is an antiderivative. Okay, basically the concept is that if f of x equals 2x, the antiderivative is any function with that as a derivative. So a good example would be x squared. The derivative of x squared is 2x. Okay, pretty straightforward, right? Okay, here's the definition straight up. A function f of x, and we often use capital X f of x, although it's not 100% standard. A function capital F of x is an antiderivative of little f of x on some interval if the derivative of capital F of x is little f of x for all x. Okay, it's exactly what you would think. A derivative is taking a derivative, antiderivative is going back to what it came from. That's all an antiderivative is. Okay, so here's an example. Cosine of x. What function gives us a derivative of cosine of x? The antiderivative of sine x. Okay? So, that's pretty straightforward. Now, let's take a look at x squared. Okay? Now, what function is going to give us a derivative of x squared? Well, it's going to have to be a function that had a derivative of something x cubed, because when we take a derivative, the power comes down. Okay, so it'll be x cubed. But then, if it were x cubed, then the cube would come down and we left with 3x squared. So it would have had to start with 1 over 3. Okay, here it is, 1 over 3x cubed. But notice something here, right? So if I take the derivative of 1/3 x cubed, you should get x squared. But also take a look. There are a couple other options. It could have been 1/3 x cubed minus a constant of 4. Because if I take the derivative of 1/3 x cubed and -4, the -4 goes to 0. And this becomes just x squared. Again, 1/3 x cubed plus 5. These three functions are all antiderivatives of x squared. Okay, so when we talk about an antiderivative, we talk about an antiderivative, not the antiderivative. Okay, so that brings up this notion of a general antiderivative. And here's how we do it. So if f of x is an antiderivative of f of x, capital F of x is an antiderivative of little f of x, then every other antiderivative is of the form f of x plus c, where c is an arbitrary constant. And the capital C is a standard. People use the letter capital C all the time when we talk about general antiderivatives, and that's pretty accepted as notation. Okay, so let's go ahead, let's go back to this problem here. Let's find the antiderivatives, so plural, of 2x. Well, we said that one of them was x squared. Okay, so if I take the derivative of x squared, then I'll get 2x. That means every other possible antiderivative will be x squared plus something, plus a constant number. So we write it as x squared plus an arbitrary constant. Okay, so that's our general antiderivative for f of x equals 2x is x squared plus the arbitrary constant c. Not so hard. Okay, so now we want to talk about the indefinite integral. Now, the indefinite integral is really the same as the antiderivative. It's just notation. So here's the notation. The notation with this integrand, we call this, is called the integrand. Okay, I can write that down. Integrand. Okay, that's called the integrand. Get rid of that now. Okay, the integrand. So f of x dx is equal to capital F of x plus c. What that means is that the derivative of this equals this. Okay? It's the exact same thing we were just doing, but now we've introduced notation that allows us to say take an integral. In the same way that we have the notation that says take a derivative, we have notation that says take an integral. So the integral of f of x dx, okay, is f of x plus c. Now this dx business, we'll talk more about it later. It looks a lot like the kind of stuff we did with derivatives, right, with that dy dx. It is actually the same idea, okay? It's an infinitesimal, if you want to think about it that way, a differential operator. So this says take the antiderivative of f of x where x is my variable of interest. Okay? That's what this is saying. Okay, it's almost like a placeholder. It says, what variable are you talking about? We're talking about the variable x. Okay? All right. So that's pretty straightforward. So if I want to take the antiderivative of 2x, or at the same time, the indefinite integral of 2x with respect to the variable x, We know that is x squared plus c. Okay, so antiderivative formulas. Let's look at some formulas here. We have a real nice formula which says that if I take the antiderivative of two functions, I can take the derivative of the sum of two functions, I can take the antiderivative of each individual function and add them together. That's what this first one says. And the second one says that if I have a number times a function, I want to take the antiderivative of that. All I have to do is take the antiderivative of the function and multiply it back by that number. These two formulas hold for both derivatives and antiderivatives. Very, very nice. Okay, now we have a whole mess of the others, and these ones you just want to copy down. This is the power rule for antiderivatives. So for instance, if I want to take the antiderivative of x squared, it's going to be x cubed divided by 3 plus the arbitrary constant. And this works only when I'm not looking at x to the negative 1 power. If I'm looking at x to the negative 1 power, the antiderivative of x to the negative 1, or 1 over x, is ln of the absolute value of x. We know we should have a sense of the antiderivative of e to the x. It's e to the x. These trig derivatives, antiderivatives, pardon me, okay, they all follow directly from the derivatives. So these ones in particular, there's no need to memorize these. As long as you have the fact that you know that the derivative of cosine is negative sine, I trust that you can figure out the antiderivative. If you know the derivative of tangent is secant squared, you've got the antiderivative. If you know the derivative of secant is secant tangent, and so on. Okay, so there's no need to memorize these separately. You should write them down today. But when we're talking about memorizing, these ones aren't going to require extra memorization. They're going to require extra recognition, but that's it. Okay, these ones, this one you're probably going to need to memorize. You'll use it a lot. And this one you'll probably need to memorize. You'll use it a lot too, so it's not going to be a big deal. Okay, let's do an example. Oh, here we go. Pretty simple example. It's almost a polynomial, but not quite. Okay, with negative exponents. I've got 3x to the fourth minus 5x to the 2/3 plus 1 over x dx. So I'm going to use my rules, and I'm going to do it the long way. Okay. So I have subtraction and addition, so I can separate into 3 different integrals for step 1. That's by the linearization, the first rule we had. The other rule said that I can pull multiples out. So 3, constant multiples. I can pull that outside of the integrand. 5, I can pull that outside of the integrand. I kind of get this nice thing. Now I know how to take the antiderivative of x to the fourth. I know how to take the antiderivative of x to the 2/3, and I know how to take the derivative of 1 over x. Okay. The antiderivative of x to the fourth is x to the fifth over 5. The antiderivative of x to the 2/3 is, I add 1, so x to the 5/3 divided by 5/3. And the 5 is still hanging out there. This 5 is that 5. Plus c is 2, so I have constant 1 for this one, I have another constant for this one, and the antiderivative of 1 over x is ln of the absolute value of x, and plus, again, a third arbitrary constant. Okay. All right, finally, we've got our solution here. 5/3 x to the fifth, I'm just simplifying here, minus this part here, which simplifies to x to the 5/3, 3x to the 5/3, pardon me, and this part, which is ln of absolute value of x, and I have 3 arbitrary constants, c1 minus c2 plus c3, so I have 3 arbitrary constants, but notice these are all arbitrary numbers. Okay, they're just arbitrary. So if they're 3 arbitrary numbers added together, that's just really a third arbitrary number. So whenever I have 3 integrands added together, I'm taking the antiderivative, I don't have to worry about 3 different arbitrary constants. Instead, I can just look at 1 arbitrary constant. Okay, all right, that's it. Pretty straightforward lesson today, and it's just going to require some practice.